Hello everyone, recently I have uploaded a text sentiment classification model, and if you go to Python Pytorch folder, you can run this main Python file to see the result. And for those of you who find it hard to understand the whole system, I've made an easier version in Google Colab, and I'm gonna give you a step-by-step explanation, and you'll be learning about how to train a deep learning model in Pytorch and do BERT semantic embedding to transform the English sentence into a low-level semantic vector. So if you are first time in Python, you can get logged in to the Google account, and once you are logged in, click Google Apps and go to Drive and go to My Drive on the left panel. And let's create a folder by right-clicking on your mouse, new folder. Let's name it as text sentiment classification. Create, and let's go into this folder by double-clicking and right-click mouse and go to more, and you can click Google Collaboratory. And if you don't see this item, then you can click Connect More Apps and find Google Collaboratory and install it. So because I'm already installed, I'll click this Google Collaboratory. So once we are in, let's name this Python ID as main. Okay. So first of all, we need to upload the dataset that we'll use for training. And if you go to here, back to where we are, you can see the link to the dataset. And if you click this, it will direct you to the sentiment analysis dataset and download it, and it won't take much. So once it's downloaded, then you can see this folder, and let's extract this zip file. And if you go into this folder, then you can see a sentiment analysis file. And if you see the contents, it's composed of 3 columns: ID, label, and the tweet. So it's a collection of tweets mapped with a corresponding label, in which the 0 denotes the positive emotion and 1 is the negative emotion, and the ID identifies the specific sample. So let's upload this file to our Google Drive. So in the text sentiment classification folder, let's create another folder called dataset. And within this dataset, let's upload this text sentiment analysis by dragging it here. So let's go back to our Python IDE. So if you go to my Google Colab code uploaded in my GitHub, so in this notebook, you can see this command, this code. So copy this and let's paste it here. So what it does, it mounts this content drive. So shift enter. So by pressing shift plus enter, it's going to run this block. So connect to Google Drive and click continue. continue. And if you click this plus icon on the left panel, you can see, let's repeat this, click and click again. You can see drive folder and click here and click my drive. And down here, you can see text sentiment classification folder and click it. And within dataset, I have sentiment analysis file. So click this and click copy path. You can click this. So if you copied it, let's data path, name of data path variable equal to R and apostrophe. So let's close this left panel and we'll read this file for line in open data path and let's print the line. So you can see it's printing in line. So let's look at the first 5 lines. Let's type CNT with 0 and increment CNT whenever it iterates loop CNT plus equal 1. So if CNT is greater than, let's come down here, that if CNT is greater than 5, we'll break from this loop. Type break. So it's giving us 1, 2, 3, 4, 5, 6 lines because it's starting from 0. So you can say that what we need to do, remove the enter symbol. So to remove, then you can see new line after every line. So to remove the new line, you can use strip line is line dot strip. Then it is going to remove the new line. See, you can see that there's no new line. So what we need for training is the label and the corresponding sentence. So let's break this by the comma. So split, we can split by the comma using line split with the argument comma with apostrophe on both sides. So print line, let's print split. Actually what it's going to give us is the 3 elements. So to get the element, we can access it with the specific index. So ID we can access it with the index 0 and label with the index 1 and the tweet with index 2. The index starts from 0. So index 0 is going to indicate the position at 1 and the index 1 is going to indicate the position 2 and so on. So ID, let's assign split 0 and sentence sent virtual. So length split sent is at index 2, so index 2 and label is at index 1 split 1. So if we print let's print this to discriminate. for each ID. So for each ID, so if you want to print ID, then it is going to print pass ID value and print it here. Print sent, comma, print label. So shift enter. So you can see ID is ID, tweet label, and from ID1 we can see the sentence, and 0, the sentence is finally a transparent silicon case thanks to my uncle, and you can see that it is positive emotion. Let's see the sentence corresponding to negative label. What amazing service! Apple won't even talk to me about a question I have unless I pay them $19.95 for their stupid support. So you can see that it's negative emotion. So how we'll train the model? So in deep learning, the technique is to show the sample and tell the machine that it is the answer is this. So in this case, show the machine this sentence thanks to my uncle, and this is positive emotion, and show the machine another sentence with positive emotion, we love this, blah blah, and map it with this is negative, this is positive emotion, and with negative emotion show the machine this sentence and teach the machine, tell the machine that this is a negative emotion. And through this repeated training, the model becomes smarter that it can discriminate between the positive sentence and the negative sentence. So let's um, train actually data create. Before we create data, because we are going to pass this sentence into BERT model. So BERT model, what it does is that it transforms this sentence into a numerical vector with filled with floating point numbers, because the computers cannot understand high-level human language. So if you use BERT model, then it understands the meaning of this sentence. So if you go to my text sentiment classification model, so you need this process. So if you declare data, we'll add the coupled sentence with label, and we need to segment the sentence into words. So here's the code and sentences. Let's first append the labels and the sentence. So let's go back to collab and sentences, labels. And what we need to do is that we need to pass this, because we are not training this ID and label columns. So if ID equals ID, then continue, goes back to the start of the loop, and it executes from this line downwards. So if you run this again, see ID, and it does not print this sentence and label. So we are going to add the sentence and label when the ID starts from 1. So let's add the sentences that append. Remember that we have declared the sentences and we call it as list, so we can add store each sentence into this sentences list, sent, and labels the append label. So let's remove these lines and let's print length sentences, print length labels. So we can see, let's go up again. Let's remove this. Let's delete this line and run again. So you can see that there are 7,920 samples. So we need to do some more pre-processing. So for each sentence, let's copy this line, come back to here, and loop for each line for the until the end of the sample. Words list actual words. So for word in sentences I, so what is going to output print word. Let's comment these lines. You can type control and slash to comment. So if you comment these lines, then the code block is not going to execute these commented lines. So here's print word, comma word. So it's breaking it into word. So let's go up and let's stop this and add word into word.append word and actual word actual words we append word and in word we are going to append the corresponding ID for the word, and this ID is different from the ID corresponding to the sentence. So let's go back to here, and you can copy these lines, come back here and up here, plus code, click, paste, and we need to import to here and copy this and here paste. From collections, import default dict and import numpy as mp, enter. And word to ID is assigned default dict of lambda colon length of word to ID pad word to ID and enter. And we are going to use it later to for bot semantic embedding. So to employ the bot, so down here, words, we need to convert into numpy array because deep learning model can only receive numpy arrays, not but list. So because the words is a list type, we need to convert it to array. So up here, let's import numpy as mp So we are using mp as an alias for numpy. So shift enter, and down here label, assign labels I, and let's append the data, the append of words, comma actual words, comma label. So if we go up here, we need to convert it into array as well, mp.as array, and because the original type is string, we need to convert it to float as well, and you need these two brackets on both sides. So down here, so let's type print. So delete these lines and shift enter. Something value error could not convert. Actually, we need to, let's copy these lines and down here paste it here. So it raised the error because remember that the label was not a number, but label was something like label ID label tree. So once we continue this ID, then we need to do typecasting. So shift enter, and if we print the length of data, we have 7,920, and we are going to use the first first 4,000 samples for training, and the first and from the 4,000 to the next 2,000 samples for validation, and the final the samples from 6,000 on as our final evaluation. So printing out length of train, comma length of validation, length of test, test, we need data here, 4,000, 2,000, and 1,920. So in Pytorch, we use loader. So let's go to here, and let's down here you can see that this here's train data loader. So let's first copy this line and go to here and paste it down here. Train data loader is get loader of mode is train, and we are going to shuffle the samples for training to preserve asynchronicity, to preserve the and let's define get loader. So up here, actually let's copy these lines and paste it here. So let's first comment these lines, and here dataset, we are instantiating it with SA dataset. So let's create SA dataset class up here. Let's go to this ID, and you can see SA dataset here, and copy this and back to main file and paste it here. Class SA dataset, and this dataset is in Pytorch library. So from torch.utils data import dataset, and let's also import data loader, which you'll be using later. So run and class dataset, define init. So for every class you need to define init method, and specifically in class that inherits from dataset module, you need to also define get item and length method. So according to the argument mode, so in case of train, it's going to return training data, and in case of validation, it's gonna return validation data. And let's define get data method. Here, copy and paste it here. So df get data of mode if mode equals train, return train data. So in this train data, we have defined it here. So lf, if it's not train and if it's validation, then return validation data, and if it's test data, then return test data. And let's check down here, data return data is get data. Let's pass mode equal to train, and let's check the length of RT data. Let's run this, run again. It's 4000, and in case of validation data, it's 2000, and the test data set, it's 1920. So up here it's correct. So we'll use this get data method in SA dataset class. So down here, if we instantiate this dataset with SA dataset of with the received mode in getLoader, in getLoader method, you can see we pass mode equal to train. So for train data loader, it's gonna pass up here the samples in the train data. So let's uncomment these lines again. So up here, so what it does, batch is sorted, batch comma key is equal to lambda x clone x o the shape o comma reverse is true. So what it's doing is it's sorting the samples within batch in the descending order. An example of this is that, let's go up. So let's declare numbers 4, 4, 6, 2, 3. and print nums. We have 5, 4, 6, 2, 3, and if we sort it using sorted function and we pass nums and key is lambda x colon x, so it's going to sort it by the comparison of the number value. In this case, XOO corresponds to up here the sample that index data index O is words and actual words. This tuple, this coupled words, actual words corresponds to XO, and the first index O corresponds to words. So it's going to sort it in reverse order according to the shape. So down here, so if we see this result, reverse is true, and print again nums. So we can see after sorting 6, 5, 4, 3, 2. So down here, what it does is going to sort. So if you want to see by fetching the sample per sample in batch, print sample O, and let's stop here or sort first, shift enter, and by running this, it's going to execute up here this collate function. So let's run this. So you can see it says SA data is not defined, so up here again. So run this, run. Because it's not giving us nothing. Let's go up and let's comment this and let's try to execute this whole code. So before that, we need to import the necessary libraries, torch and pad sequence. It's in pad sequence. It's in torch.nn.utils.rnn. So here, from torch.utils torch.nn.utils.rnn import pad sequence, execute and run. So to execute these lines, so what we need to is that down here we need to fetch per sample in train data loader, and what it returns is labels, both sentences, both sentence types, both sentence attention mask, labels, comma, both sent, comma, both sent type, comma, both sent attention mask, print is, let's name it as batch, for batch in train data loader, batch. So print labels. So we need bot tokenizer. So here, let's check bot tokenizer. Is bot tokenizer the from pre-trained? Copy this up here. Let's go up and let's check where bot tokenizer has been used. So here's encode plus encoded bot sent is bot tokenizer. The encode plus of text. So this text is the text that the original text. So let's comment these lines and let's check what we are passing. So print text, print text, equal signs on both sides. So shift enter and we'll check it just to check the results. So up here we can see by Sony. So this is the sentence, and let's go up and let's I guess its label will be the negative emotion. Maybe print labels, and let's see what it returns. It's the beloved, or so the beloved corresponds to the positive emotion. So it's giving us different samples because it's shuffling. So let's go up again. So let's let's check if we don't if we set it as false, shuffle false, and go up, enter, shift enter, shift enter, shift enter, and excuse me. So excuse me, it has negative emotion, and if we run again, it's giving excuse me again because we are not shuffling, so it's giving us the top sentence in the corresponding batch. So because we need to shuffle every batch, let's set it to true, and shuffling the training data. So it let's go up again. So it's required shuffling the training data for effective generalization. What it means by effective generalization is that the model should predict the corresponding emotion on unseen samples. So to ensure that, we need to allow shuffle the training data. So let's delete these lines again. So now you know that this text is the original text. So it's gonna we'll pass the original text to encoded but sentence. Let's check the code again. The encoded but sent. Let's go back to here. Let me just a sec. comment this and let's see print text. We can see the text so up here, and the corresponding labels are in the labels list up here. So what we are doing is that we are passing each text to this encoded BERT sent BERT tokenizer, the encoder plus, and we pass this text here, and max length, this sent length is calculated up here, and with add a special token set to true and pad to max length equal to true, and we append and store this encoded BERT sent into BERT details, and we can, after it returns encoded BERT sent, we can fetch the BERT sentence and BERT sentence type, BERT sentence attention mask by accessing them with input IDs, token type IDs, attention mask. So down here, we pass this collate function to data loader, as you can see here. So up here, this collate function down here does this works, and it finally returns labels, BERT sentences, BERT sentence types, and BERT sentence attention mask with batch size 64. So if we set it to 32, then it's going to give us 32 samples per every batch. Actually, let me repeat that. For every epoch, it's going to give us 32 samples. So run again, and if we type labels.shape, up here we need to delete the print line. Let's shift enter and again. But BERT tokenizer, it's raising this error that BERT tokenizer is not defined, so it's here. So BERT tokenizer is in transformers, and let's go to this code, and from transformers import BERT tokenizer, copy, and up here paste. So once it's run, let's run it again, and we can see it's giving us 32 samples per each batch. And if we go up and if we change it to 64, run, now it's giving labels in 64 within a batch of size 64. So with this BERT sentence type, BERT sentence attention mask, we can employ BERT model by passing these arguments. So let's go to see the BERT model. So you can import BERT model from transformers and BERT config BERT model here, back here, and up here. So let's import from transformers, import BERT config BERT model, run, and here BERT output So let's copy these lines and back to our code. So you can call BERT model to return the BERT output, and you need to pass the BERT sent fetched from this batch earlier in the train data loader. And BERT model input IDs BERT sent, attention mask, BERT sent mask, BERT sent. Let's remove this attention mask. So now it's spelling correct, BERT sent mask, and pass token type IDs with BERT sent type. And let's declare BERT model. BERT model, copy this and our notebook. BERT model is BERT model from pre-trained BERT model, which is declared up here. And from pre-trained BERT based on case config is you pass BERT config, which is let me check whether have I don't think I have declared this BERT config. So go here and BERT config, copy this and paste it here. So get BERT config with BERT config from pre-trained BERT based on case with output hidden state set to true and run this. And if you run this again, so pass BERT output returns, and you need to access BERT output with index 0. And let the batch size, you can retrieve it with BERT output shape with the first index of the BERT output. So the masked output, you need to compute the masked output and the mask length and the BERT output. So you touched up more BERT sent mask on schedule to 2. So you can follow this code. So what we are interested in is the final BERT output, and it's gonna have length dimension 768 BERT output shape. So standard BERT output has 768 dimensions. So let's check it whether our BERT model is correct. Let's wait a sec. So you can see it's outputting BERT output with 64 samples, in which its dimension is 768. And now let's see their values. Print stop this BERT output, and we want to stop here, assert false. So you can see each BERT output with 768 dimensions are filled with floating point numbers. So what we are going to do is that we are going to use LSTM layers to train to adjust these values so that actually not these values. So we are going to train LSTM layers to find the weights that can well map these values semantic embedding vector to the corresponding label. First of all, let's map this into a function. So here I'm going to declare what output. Actually, rather than here, um, okay, let's get what output and copy this and down here you need parameters in which bot model and bot sent type, bot sent mask, and finally we need to return bot output. And let's get bot output by calling get bot output. You need a colon at the end of the function definition, and bot output get bot output plus bot model. Copy these lines and paste it here. Let's check bot output the shape. Run this and again run. Bot model is not defined. Let's go up. So let's change it. Here was spelling mistake. Again, run. So now it's we can see that it's giving us correct value, and let's check the values inside again once again. So it's properly giving us the values. So for the time's sake, I'll just go to my code I've uploaded earlier in this Python Pytorch folder and copy and paste and show you how we can train our deep learning model with LSTM layers. And actually, I have let's copy these lines first. In my earlier videos, I have uploaded video that explains step-by-step explanation for this LSTM in Pytorch for multimodal sentiment analysis. And I'm going to upload the code maybe up here, and let me know if you need the link. So back here, anyhow, you can just adapt this model and paste it here. So if you have declared LSTM here, and let's shift enter, and we need to declare my model as LSTM. So up here, we have declared the LSTM model, and up here, let's remove this config. We will not use this argument. Let's change this code a little bit. So class LSTM init method super LSTM sub.init RNN. We initialize RNN with the nn.lstm and set the heading size. Let's set it to 16. And the input size of RNN is 768 because the BERT, if you remember, the dimension of BERT was 768, and we are going to downsample it to the hidden size of 16 units, and let's set it bidirectional to false. And RNN again, now this time it's LSTM hidden size is 16, so and the output size I'm going to set it to 16 again, and let's set bidirectional to false, and let's remove these lines. And down here for the function, remove. So what we are going to receive is bot output. So assuming that we pass the bot output to this for the function, batch size is going to be x dot shape o. Let's check print x dot shape. Actually this is bot output, and let's stop the code from here. Enter, shift enter, and prediction my model bot output, and let's see print pred that let's remove. If you shift enter, so you can see 64,768, and if you go up, so bot output, so it's receiving forward function. So down here, the batch size is going to be 64 because up here x the shape returns 64 comma the shape of this, which is 64 comma 760, and we are accessing and the first index. So with this batch size, let's remove these lines. So what let's name it as occurrence text, because what we have received is actually the text information that we have embedded into a low semantic vector with bot. So x occurrence text is x, and we feed this occurrence text into this RNN occurrence text, and let's check the shape of h1. Assert false. So you can see the hidden size is 16. So up here again, let's feed this hidden vector into the second LSTM layer, and let's check the hidden size of h2 the shape. So it's giving us 1,16, but note that we have lost the channel information. Actually, it was not channel, but the batch size. So we need to expand the axis by 1 for to hand it as the channel axis. So up here, before we feed this utterance text into the RNN layer, let's x dot coach dot case x comma dimension equal to 0, not case on case. So what it'll do is that it's going to print utt comma utterance text the shape assert false. Let's see utterance text the shape. So utterance shape is 1,64 by 768, and the output is giving us 1 by 64 by 16. So we need to sketch it again so that we have 64 by 16. So up here again, let's unsketch h2 touch the sketch h2 comma dimension equal to 0. So what it'll do is that let's wait a bit to see the result. You see the first axis has gone, and remember we are predicting two classes, negative or positive emotion. So we need to downsample it to two categories. So up here, O is self the FC of O, and this fully connected layer is declared up here with here and then the linear. And because we are passing 16 units, change the input size to 16 and return final output O. And let's delete these lines and run. And let's check the shape of the thread and its value. Print thread. So local variable O reference before assignment up here. So not O, it's H2, should pass H2 to fully connected layer and run again. Let's run again. It says train data loader is not defined, and let's go up. Let's run from the top all over again. Enter, shift, enter, shift, enter. Yeah, it's learning now. So what we are trying to check is the shape of the prediction and the value, and down here we can see the result, and up here the shape is 64 by 2, and we can see their respective values. So what these are, you can think of it as the probability. So actually you need softmax, but um but just in this case, let's say that if this value, because in this case for this is prediction, this is giving a prediction for this sample, and because this number is higher, it indicates that the model is predicting as 1. So if the left value is higher, then it's saying that the given sentence is 0, or it's the second value is higher than the given sentence is 1, which is negative. So what we are going to do is that we are going to train this model to predict correct values, in which it gives higher left values for sentences with 0 labels, which is the positive emotion, and for the negative sentence, it gives the higher values for the second column. So how we'll do is that we are going to do it with the cross entropy loss function, and the optimizer. So let's declare criterion. Let's declare the loss function as, and then the cross entropy loss reduction is equal to mean, and optimizer, we are going to use Adam optimizer, optim the Adam filter. Let's just copy the optimizer and go to this folder and in solver file I declared optimizer. So let's copy this and go to main file. First let's declare from torch import optim and filter lambda p colon p that requires gradient for the given my model parameters, and I'm going to set the learning rate to 1e minus 3, which is this value is 0 point learning rate is 0.001. So for the prediction, we compute the loss function. Loss function. Let's go to this code, and if you see that we pass the prediction first and the true label. So prediction, comma, and labels. So we do backpropagation. So this backpropagation process drives this model to have lower loss. So the loss is lower than the statistical measure between this prediction and labels is closed, so that the model is predicting correct labels for the given sentence. So let's check the loss values. And what we will do is that we are going to iterate this for n epochs. Let's up here and click run again. Loss. So we need to typecast labels. Labels as labels.as type. Let me check in this code again. So labels.type torch.long tensor. And run again. So what we are going to do is that we are going to compute the loss, average loss for each epoch of all batches. So select these lines and press tab, and up here for E in range, the number of epochs, let's define it as n epochs, 500, and for E in range, n epochs, and train loss, and let's append this loss, train loss dot append loss dot item, and after each epoch we are going to print the average loss, mp the mean of train loss, the format. We are going to print it to up to 4, the 4 floating point, 3 floating point. And for fast training, let's change runtime type to GPU. Okay, save, and let's go up and run again from the start. Click and enter, shift enter, shift enter, shift enter, shift enter, shift enter, and shift enter, shift enter, shift enter, shift enter, shift enter, enter, shift enter, shift enter, shift enter, shift enter, enter, and run, 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 run. So up here I've got I need a colon, run again. Here I need right parenthesis, run again, and epochs. So here's spelling mistake, and epochs, and run. So let's see the result, whether the loss value is decreasing through the epochs. Actually, we need optimizer, so remove these lines. And here, if you see the low stop backward after low stop backward, you need to step optimizer the step, copy this, and up here we see that we declared optimizer the step, again run. Let me check the code again. Back to our notebook, and better I'll skip this training process. For final, for time's sake, let's set this number of epochs to 10 and stop this, and let's print epoch to observe in where we are, and let's copy the evaluation method I have defined earlier. So copy this method and copy, and up here paste, and evaluation so it's raising error if mode is not mode is none, and we are changing it to evaluation, and here's why true list and prediction list, evaluation loss, and if the mode is development, the data loader is the self, the development data loader, and if it's test, then we assign the test data loader. So up here, let's remove this data loader, and up here where we declared train data loader, let's declare development data loader and test data loader as well. Development data loader is get loader of mode is development. It'll be used for validation, shuffle false, and test data loader is get loader of mode is test, shuffle is false. And let's go to let's run this and go to get loader shuffle is so in this example, I'm not going to use development data loaders. Let's only use test data loader and train data loader. So up here, let's run this again, and I'll just show you the final evaluation result. So once I finish training, let's let's print the accuracy, and let's go here how I have printed. So eval mode, go here, and if I type eval mode is test to print true, let's find eval, remove this stuff, and model.eval y true y pred evaluation loss mode equals. So let's remove this, and if mode is test data loader is test data loader, and if I'm to print, then I'm loading the model. So let's comment this, and I'm just show you the evaluation result after final training with torch.nograd for batch in data loader. Model.0grad. We fetch the sentence, the label. So up here, see, we let's go to train data loader. We fetch labels %, and this copy this line and go to eval function. Fetch this. So to use GPU, actually, although we have changed the runtime type, we to check again to GPU, we haven't used it to CUDA. So yeah, so center is, let's start CUDA model, and up here let's go to train data loader again. Code, and let's go to where we declared my model. So the to the CUDA and run, and here let's go to train data loader, let's convert it to labels. Labels.CUDA bot sent is bot sent.CUDA bot sent type is bot sent type.CUDA bot sent mask is bot sent mask.CUDA. So I guess it's going to run a lot faster. So labels, let's run again. CPU encoder. Maybe I need to convert the bot model. Bot model to CUDA. Shift enter and shift enter again. Enter and shift enter, shift enter. And down here, training, enter. So it's running for epoch 0. Let's see how it goes. So I'm going to run it just for 10 epochs, and while it's running, let's go up to our evaluation function and let's change this code to make it correct. My code model.0grad labels bot sent and labels. We first change the type to labels.type torch.long tensor and labels.CUDA bot sent. Copy this. CUDA bot sent type. CUDA and bot sent mask. CUDA. So remove this line. Label is to GPU of label.type of torch.long tensor. So it's correct. So prediction is my model of bot sent, bot sent type, bot sent mask. Loss is loss function of pred, labels, and we add the evaluation losses, which has been declared up here, eval loss, and down here we append prediction, and for calculation we need to detach it to CPU from GPU by true.append of label.detach.cpu.numpy. So we calculate evaluation loss down here, mp.mean of eval loss. So if we go up here, so it's averaging, it's calculating the mean of all the evaluation losses, and concatenate vertically and prediction, concatenate vertically, and then we find the higher value. It returns the index which has the higher value in my prediction, and we calculate the that equals the to the label, true label, and the predicted index. And if they are equal, then it returns true. Otherwise, it returns false. And it sums all the values of true and divided by the number of corrects times 100. And if the argument is to print is true, then it's gonna print accuracy and return evaluation loss, and the accuracy still appear. So if we pass to print to true, then it's going to return the evaluation, the accuracy. So down here, let's just see how far it has gone. So you can see that the loss value is diminishing, which means that the training process is going well. 0.580, 0.425, 0.343, 0.337, and although there was some increase, anyhow, let's run this to check the accuracy. Mode is evaluation. We need to run this evaluation method again, and down here, let's see the accuracy. lstm.fold text to positional arguments before given. Let's go to the eval method. My model. So my model actually outputs only, it receives only bot output. So if you go to lstm plus lstm plus lstm in fold method, it only receives the bot output. So in evaluation method as well, we need to return only bot output, but output, and this bot output we can return it with bot output function and find. So to find, you can press Ctrl and F eval bot get bot output, and let's copy this and go to eval function, and down here bot bot output align, get bot output of bot model, bot sent type, bot sent mask. So run this again, and down here let's check the accuracy. NumPy the n dimensional array object has no attribute. Up here, let's check pred, print label. Let's check the error again. Evaluation. Let me come back once I fix this error. So I have fixed the error. Actually, earlier I had a spelling mistake. I wrote it as a label. So if you enter this and down here, you'll get, if you run this, it's taking a bit of time. Up here again. So this evaluation method is still running. Um, so back here, um, enter. So here, why true the append of label.detach? It gives attribute error numpy the n-dimensional array object has no attribute detach. But if we go up and correct the label to labels, because I have named it as labels, so enter again when it's run and come back down. So if we run again this method, note that the mode is test, and on the unseen samples of the test data on which above here of the samples appear 1920 samples, we are able to get the classification accuracy of 81.46%. So this is all for today's video, and up to here you have learned how to create a deep learning model in Pytorch and how to use BERT pre-trained model for semantic embedding of English sentences for text from the text, and train a text sentiment classification model by via the BERT semantic embedding of the text to and mapping them to the corresponding positive or negative emotion. So we've done binary classification here, and this is all, and I want to finish off here. Thanks for listening. Goodbye.